So in this video, I thought we'd go ahead and take a look at the 7-segment display board here. If I can grab my pointer. This little board down here. As you can see, it is doing an up count in hex. There's a 16-bit counter running that's counting from 0000 to FFFF hex. That counter is incremented, I believe, every 5 million clock cycles or 25 million clock cycles. I don't remember exactly, but anyhow, it's producing an up count. That value then gets mapped to the 4 displays. These displays are multiplexed, so each display is on for 10 milliseconds, and it just sequences through. The pins for the segments in each display are actually common across the displays. So right now it's outputting the bit pattern for a 0 and turning that display on, then the bit pattern for a 1 and turning that display on, then the bit pattern for a 4 on that display, etc. And there's a 10 millisecond delay between each one, so it's every 10 milliseconds jumping to the next display in this order. So it's going left to right. We've of course got our USB plaster hooked up to the JTAG. I've gone through the Verilog code and heavily commented it and believe I understand it. And I will take a look at the code and see how it all works together to make this happen. So I thought we'd start out here looking at the pin planner for the 7-segment project, the demo project that came with the board. And it's pretty much what we saw before. Clock on pin 18, that's the 50 megahertz input. The reset button on pin 61. There's then the 7-segment display, which is mapped from this bit 0 to bit 7. This is the decimal point, and then it works its way down through the individual segments. I'll show you a mapping of that later. And then there's 4 more outputs that select which one of the 7-segment displays is enabled. The displays are multiplexed in this code, so only one of the 7-segment displays is on at a time, and then it just scans through them all. So the bit planner is pretty much what we expected. There's 2 inputs, clock and reset, and then everything else is outputs. The little 7-segment display board that came with the EPM1270 plugs into the 16-bit I/O connector, and it is wired directly to these pins via the layout of the little PC board. So let's take a jump into the actual Verilog code for this. And again, I'm going to throw out my standard disclaimer. I am not a Verilog developer. I've only been playing with it for the last few days. I'm making some assumptions here. Some of these may be incorrect. If they are, call them out in the comments. We have 4 source files, or 3 source files, sorry. The display, select 4, and seg7. Let's jump straight to the seg7 and start kind of from the bottom up. So the seg7 module has an input that is 4 bits wide, and that is the hex value for the position we want to display. So if this is on the right hand digit, these 4 bits would represent the value we want to map to that 7-segment display. So this would run from 0000 to 1111. As I say here, it runs binary. This becomes a lookup that looks up in this table. So what we do is we take the data value that came in, that 4-bit value, and we say, is it a hex 0? If so, the pattern we're going to send to the 7-segment display is this bit pattern right here. This is a binary value. It is 8 bits wide. And it's mapped kind of as I've drawn up here. The 7-segment display segment nomenclature is A, B, C, D, E, F, G. That's a standard. The A segment is mapped to pin 94, the B to pin 98, the C to pin 86, etc. around the display. And then the decimal point is on 74. If you look at this a little further, in this 8-bit value here, so there's a binary 8-bit value, this first digit right here is to the decimal point. This next digit goes to the A segment, the third digit goes to the B segment, etc., all the way across. So if we take the bit pattern here for all zeros, or for 0, we would have the decimal point off, that first 0. we would have segments A, B, C, D, E, F on. So A, B, C, D, E, and F are on. And this last bit here is for segment G, which is off. So we get a 0. And if you take the bit pattern for each one of these, say we take the bit pattern for the number 1, we would have segments decimal point A, B, and C on. B and C on give us the number 1. So these bit patterns represent what segments in that 7-segment display are enabled. As written, they have the decimal point on. I've changed this most significant bit here to be 0 just to turn the 7-segment display off. Just to kind of recap, this 4-bit data value comes in. There's a case statement here that says take that 4-bit value, and if it's a hex 0, assign this bit pattern. If it's a hex C, assign this bit pattern. Because it's 4 bits wide, and this goes 0, 1, 2, 3, all the way up through F, it should never come down to the default. I mean, we should never get here. It's just good coding practice to have a default. I don't know if that's mandatory in Verilog. And basically what this is doing is again, always is running. Let me actually add a comment here on the always. Just because I missed a comment, I'll steal the comment from a different block of code. We've looked at the always statement before. So what this is saying is, well, that's not true. Let me remove that. I don't actually know. Oh, getting a text message. I don't actually know what the asterisk here means. I'm going to have to research that. I don't think this is running constantly. I don't know. This right here I don't fully understand, but I know this creates a lookup table. The seg2 is a little storage, is a little 8-bit storage register inside that this pattern gets saved into, and then seg is what is mapped back to the previous code. So then it assigns seg in a non-blocking manner to the not of seg2. Oh, that's interesting. That actually makes sense. We've defined this here to be a 1 equals on, but in reality, electrically, we're putting a 0 on each one of these segments to turn it on, and then there's a transistor that passes the +5 that is, or the +3.3 that's common to them all. So this just takes care of inverting the bit pattern. So this was done to make this easier to read. We interpret this as 1s being on, as I described earlier, but in reality, every place there's a 0 actually going to the 7-segment unit it's on, and the not here takes care of inverting those bits. So that's an interesting bit of code to make it easier to read. So we have this routine down here. I'll call it a routine. I'm not sure of the proper name. This module that assigns the appropriate bit patterns. We then come up to the next block of code here, and this takes care of multiplexing the displays. This has, I'm going to call it a template. I'm not sure if that's the proper term, but this knows that there is this 7-segment module here, this guy we just looked at. He's aware of it here, and I am under the belief here, and again, correct me if I'm wrong, that data and seg to it are mapped to these register variables defined in here. So as this runs down here, it's accepting that data is an input and it's that seg is an output, and I'm assuming this is some kind of pointer notation maybe that says take these 2 register variables here, and the data one comes in here and the output one is there, process it, set the appropriate bit pattern, and so this will keep the bit pattern and segment set depending on the bits here in data. I hope I explained that well enough. There's a 1-bit register here that is a select clock that we'll look at in a minute. We then have the module that actually multiplexes the displays. and it says trigger me on the positive edge of the clock or the negative edge of reset. If the little reset button is pushed, and remember the logic here, if we push the button down, that pin goes low. So a not of a 0 or a low becomes a 1, and a 1 represents true. So if this condition is true, we're going to set the count 1 variable back to 0, and we're going to set the clock back to 0. A couple other things here to talk about here. This count 1 is used in this timing loop to control how long each display is on as they're multiplexed. Let me actually add a comment here. So essentially, for the multiplexing, we have another routine down here that rotates through the 4 7-segment displays. Again, it's triggered on the positive edge of this, so that's interesting. I just made that connection on the. This comment is incorrect. On the cell clock, positive edge or the negative reset. So this select clock is a single bit, and what this statement here does is say assign it to the not of itself. So if it's a 0, it'll get assigned to 1. If it's a 1, it'll get assigned to 0. And so it's turning that into a little clock pulse. And what this code is saying is every time this is assigned to a 1, we're going to run this little module, or this little module is going to happen. If we're in a reset condition, we select the selected one of the 4 7-segment displays to the one we're going to talk to. Else, if we're not in a reset, we say if the selected digit is the right-hand most one, go ahead and set it back to the left-hand most one. So these 4-bit positions here represent each one of the 7-segment displays itself from left to right. And so this is basically just making this little 1 walk around here, and I've actually kind of drawn this out. Each time this triggers, if the bit pattern is 1000, it gets shifted to 0100, and then the next time to 0010, and then 0001, and once we've gone to the right hand digit, we want to come back to drive the left hand digit again. So this little block here is producing this output in that little register variable, that little 4-bit register variable. This little line right here is what actually is taking care of. So we come into here with this bit pattern, and this is saying take that bit pattern and shift it to the right 1 bit. So these 3 bits, let me see if I can select them here, get shifted down to these 3 bits, and it will 0 fill from the left. And that's what is actually causing this 1 to walk across the 4 positions, and the 0 fill is what's taking care of adding the 0 there, the 0 there, and the 0 there. It's just a pretty standard shift. So this right here, seeing a typo, this right here is essentially saying which one of the digits is selected. You know, left hand, next one, right hand, and just loops through them. We then want to select the appropriate 4 bits for the segment being driven. So let me step back here. There's this data variable that is 4 bits wide. Coming into this is a register that is 16 bits wide. So 0 to 15 is 16 bits wide. This is simply a counter. It is counting from 0000 hex to FFFF hex. Once it gets to FFFF hex, the next increment will cause it to roll over to all zeros. Technically, it produces an overflow because it can't count any higher, but we don't care. So this is just a 16-bit number, 16-bit bit pattern that is counting from all zeros to all ones. So what this piece of code here is doing, and I don't understand this syntax. This comment is incorrect. This is what happens when you actually talk this stuff through. So what this is saying is if the segment that we've selected, so of the 4 7-segment displays, this variable here, is the right hand 7-segment display. Take bit positions 0 and 3 and move them into data. If it's the next digit up, take the bit patterns or the bits from positions 4 through 7 and load them into data. So data is going to contain either these 4 bits or these 4 bits or these 4 bits or these 4 bits, depending on which the 4 7-segment displays we want to talk to. There's again a default here. It should never get to this. I think it's just a good coding practice to have it. We're then taking this data here, so the 4 bits from that binary up count are being mapped through to this module here, and then it's using that to select the actual 8 bits for the 7-segment display pattern. Again, this is taking these 4 bits and putting them into this 4-bit variable, or these 4 bits, or these 4 bits, and putting them into this 4-bit variable. And you can see up here data is a 4-bit register. Another comment I'll make here is this count1 variable is a full 32 bits wide. However, it only counts up to 50,000 decimal. And if it gets to there, it then rolls over and toggles the clock. And this again is producing apparently a 10 millisecond display that says once we get to this count, move to the next digit. We do that by the toggle here. Actually, I get how this is working. So let me step back a little bit. This 50,000 count gets us to 5 milliseconds. So when we get in here and say the count is 50,000, we toggle the select bit. The select clock. Then when it gets to 50,000 again, we toggle it again. So say the first toggle took it to a 0. Then we counted to 50,000 again. The next clock took it to a 1. That 1 is captured right here, saying when it makes the transition from 0 to 1, this happens. So this is really producing a 10 millisecond delay. It leaves this pin 0 for 5 milliseconds and then 1 for 5 milliseconds. So it's producing a nice little timing, a little square wave. If we haven't counted to 50,000 yet, we just simply increment it by 1. So it starts at 0, 1, 2, 3, 4 until it gets to 50,000. To represent 50,000 decimal, we really only need 16 bits. 16 binary bits can represent the value from 0 to 65,536, or from 0000 to 0000 to FFFF hex. So in my opinion, this is really 16 bits wider than it needs to be. By doing this, however, you could slow the multiplexing down if you wanted to by getting a value here greater than 65,536. As implemented, I think this would be fine at 16 bits, but I'll leave the code as is. Hopefully this makes some sense. Again, kind of looking at the hierarchy here, every time the clock on pin 18 makes a negative to positive transition, this occurs. That's occurring at 50 megahertz. So when it's counted to 50,000, that would be 5 milliseconds of runtime. Toggle the select clock, count to 50,000 again, which is 5 milliseconds. Toggle the clock every time the clock toggles from a 0 to a 1. This happens. If it's reset, it just resets us back to the leftmost digit. Otherwise, it takes care of rotating this bit through each one of the 4 positions and then back to the left position. This is then taken care of by looking at which one of the segments is displayed, is enabled right to left, getting the appropriate 4 bits from that 16-bit up counter. And finally, this routine here is saying for the value I've got in there, bring back the bit pattern for the segment display. We then get to the top where all of this kind of starts. And as I said, this module controls the 16-bit up counter. I'll put a space in there and make it read a bit better. And the delay between up counter increments. So we have a module here. We're telling it that there's a reset pin, a clock pin. There are 4 pins to select which one of the segments is being, or which one of the 7-segment displays is enabled, and a mapping of the segments. And if we go back here, we will see that seg here is this little group of 8 pins, seg 0 to seg 7. And that's why this says 0 to 7. This is an 8-bit output that maps to these 8 entries, that maps to these 8 pins. There's also a 4-bit that selects 0 to 1, which is selecting one of the 7-segment displays, and it comes off these pins. We looked at this a minute ago. And this is basically saying on the positive edge of clock or on a reset, if we've actually gone into a reset condition, the button's pushed, we're going to start the number over at 0 and the count 1 over at 0. Count 1 is controlling delay between up counts. If count 1 has reached 25 million, we assign the numeric value of the up counter to its self plus 1, so it's going to count 0, 1, 2, 3, 4. And we set count back to 0. Else we simply increment count. So this will come in and say count is 0, increment it to 1, come in, count is 1, increment it to 2. And when finally it comes in at 24,999,999, it'll increment it to 25 million. The next time it comes in, it says count is now 25 million. Increment our number counter and start it over again. This block here then maps these various registers and pins, etc., into this guy. You'll notice that this clock, reset, number, select, and segment is in the same order as this, clock, reset, number, select, and segment. So I'm believing these little blocks here, again I'm guessing, are what tie the various code in these modules together. I do believe you could put all this source in one file if you wanted to, and you wouldn't need these because it would all be in scope within that file, so it would understand how those modules are tied together. I could certainly be wrong on that. So hopefully this makes some sense. We've looked again at the pin mapping, which maps us to the physical hardware, clock and reset, etc., to the code that actually drives the system. Every 25 million clock cycles, we increment a number. That number gets incremented. It comes through here. That number appears here. We, by looking at each group of 4 bits in that number, look up through data here the bit pattern that should be displayed in that position. And this all runs in the hardware. So there's a couple things I'll have to research here, and once I understand this here, I'll come back and add a bit to this video to explain what that syntax actually means. Anyhow, I hope this helps. In here I did add some comments that show, just to help explain this, that if we are on the rightmost segment, we're grabbing those 4 bits out of that 16-bit stream and putting them in this variable. If we're the next digit over, we're grabbing these 4 bits and again putting them into this 4-bit variable. So those 4 bits are grabbed and mapped into this 4-bit variable. We can see here that it's 4 bits wide, etc., etc., where this represents that number register, which is a 16-bit register that's just getting incremented by 1. So hopefully that makes a bit of sense. This does seem to run. I'll go ahead and save the comment changes we made. I'll compile. It wants to save all the files that I made changes to. And we'll let this crank along here. You say this is making a little bit more sense to me as I work my way through it. We can get in here and watch it do its thing. There's a number of steps it takes. Oh, I've got a syntax error. So Verilog HDL statement at select for near text always. know what that S right there is. I haven't printed this out to know what it looked like previously. I think that's just a mistypo or a typo on my part. Must have touched the S key by accident. So this is kind of cool to actually see it catch an error. If you noticed here, I double clicked on the error and it took me to that file and highlighted the line where it believed the error was. As is often the case, as it said here, it's near text always. So the line above here where I had that random text S typed in is what caused the error. So don't always assume that when you get an error it's on the line that becomes highlighted. It might be, but you might need to look up to catch it. And here, let's try to compile this again. That's the first actual error I ran into with all my changes here. We'll let this compile. I just fully expected to be able to double click the error and get to the source file and the line in it. That's pretty standard for an IDE. Looks like we've got past that error. I believe someplace in there I added an S in one of the comments and I must not have had the cursor in the right position. So we'll let this continue to chug here. And it believes it was successful. I can bring up the programmer. We can send the code down to the 1270 chip. And we're good. And it is sitting here running. I can see the 7 displays counting up D, E, F, 10, 11, 12, etc. So it is running. Let me shift this back down and bring out the hierarchy here and see if I can figure out where that S, L, E, C, T. Select the appropriate 4 bits for the segment being driven, rotate through the 4 7 displays, actually multiplex the displays. It's kind of a misnomer. This is more of the timer to multiplex the displays. The positive going edge on cell clock is used, SUD is used to drive the apologies for the keyboard noises. The microphone's sitting slightly above the keyboard and they're on a common surface, so I know it does pick up the clunk, 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 clunk. Apologies for that. Module controls, I bet I was trying to put it right there. So anyhow, I'll save this out. I will go off and research this syntax. I'll come back in a minute with a follow-up here, and we'll go from there. Okay, so I did some reading here on this always syntax here and found a great little article, and it basically says that syntax was added in Verilog Standard 2001. Basically, I'll read this, although you can read it as well. An incomplete event expression list of an event control is a common source of bugs in register transfer level routines. The implicit event expression @ is a convenient shorthand that eliminates these problems by adding all nets and variables that are read by the statement, which can be a statement group, to the event expression. So how I interpret what this says is anytime, so the net we have here, a net can be one pin, it can be a group of pins, it can be whatever you want. A net is just simply, like I say, one or more pins or wires inside of the description of the code or whatever. What this is saying is any time there's a change, in this case on the 4 bits that is select, let me find where it's defined here. right here. So anytime any of the 4 bits in this register change, this will reevaluate and update number. So that's actually pretty cool. So if we change the bit, the pattern in select here, or we change it here, or we change it here, any edge transition in here from a 1 to 0 or 0 to a 1 will basically fire this or trigger this, and it'll do the update automatically. That's actually really cool as I look at it and understand it. It makes sense to me. I'll get the comments updated here. I believe we had one other case of that syntax someplace in here. Let me see if I can find it. We had the one here, and I know I added a comment with 3 question marks elsewhere. Excuse me. Right here. So what this is saying is anytime data, so anytime any of the bits transition from 1 to 0 or 0 to 1 in this group of 4 bits, this gets reevaluated. So that's really pretty cool. You could go in here and basically say in here always, I'm not sure how you'd actually say it, on the negative going edge data bit 1 or the negative going edge data bit 2, etc., or the positive going to trigger this. And it would be easy. You've really got 4 bits that can transition 1 to 0 or 0 to 1, and I think syntactically I'd have to put in 8 conditions. Bit 0 going 1 or bit 0 going 0, or, and as it said in the description, it'd be easy to miss one of those and get a bug. And this basically just says anytime any bit in this changes, boom, this evaluation happens. That's really pretty cool. So anyhow, there's a quick update on what I discovered researching this. I'll get the comments updated here. I hope this was useful. This has been very useful for me in researching this and adding the comments. And it's always really useful for me to come back and kind of try to describe what I mean in the comments and how I'm interpreting the code. As you saw, I caught a few commenting errors. I actually learned a couple things looking at it. I hope this has been a good bit of tutorial for you. I promise you that I will get the updated code up on the ShadowTron.com blog, hopefully in the next day or two. So you can download these projects yourself and pick up the comments. I'm thinking about moving on to another project where I'm going to take a couple of these and combine them, maybe mix the joystick code with this code here. And that could actually be modified to every time you use the joystick, it updates a counter kind of thing. There's all kinds of things we could do here that would be interesting. And again, there's a ton of gates, about 4,000 gates equivalent in this, the EPM1270, and we can build some pretty complex things that can be completely independent of each other or dependent of each other as we have here in the code. So I'll think about maybe trying a couple of things I'm thinking about and getting a good description up. Anyhow, again, I hope this video was useful, and we'll talk soon. Bye.